Hello everyone, greetings from VJEC JYOTHI Institute of Engineering and Technology. This is Manohar Reddy, Department of Cybersecurity, Data Science and AIDS. Today in this talk I am going to discuss about the deadlock avoidance techniques. So what is meant by deadlock and what is meant by deadlock avoidance, deadlock necessary conditions, all the things we are going to discuss in this session. So what is meant by deadlock? Generally deadlock occurs in the operating system component process management. So the process management comes for the topic only on the basis of processes and resources. So in between the processes and resources, the deadlock will occur. So what is meant by deadlock exactly? So the deadlock is a situation or collision or condition. We can say that it is a situation or collision or condition. But where it occurs in between the processes and the resources. In between the processes and the resources. So here, deadlock is a situation or condition in which a group of processes are, that means more than one processes are blocked forever because each process is holding some resources and waiting for other resources that are held by another process in the group. That means when one process is assigned with the resource R1 or one process is assigned with the resource which is already allocated to the next process, still the process is looking for the next resource. That means one process is assigned with one resource and again it is looking for another resource. And similarly, the resource which is already aligned to the process, still it is looking for another process. So this situation occurs. That means one process, two resources, or two processes, one resource. So two resources are allotted and two or more processes are ready to occupy it, or one process is allocated with the resources. So here the condition occurs, the situation or condition in which group of processes are blocked forever. So because each process is holding some resources, that means this one. So this is assigned to the process P1, but still it is the P2 is waiting for the resource R1, right? So already resource R1 is assigned to the P1. It is assigned to the P1, that means it is allotted, but still the process P2 is trying to allot this resource R1. So that means it is somewhat difficult, right? So there the situation occurs. In the same way, the process R2, resource R2 is already assigned to the process P2, but still process P1 is waiting for the resource allocation. So at this moment the situation occurs, the collision occurs. That means one resource are trying for the two processes. One resource is trying for the two processes. Already the process is assigned with the resource 1, but still it is looking for another resource which is already handled by another process. So there the situation comes. So that is why we are mentioning this one. The process is holding some resources and waiting for other resources that are already held by another process in the group. The same thing. So the deadlock system model in OS uses resource allocation graph as a one technique, and that is also called as wait for graph, that represents processes and resources. It's showing which process holds which resources and which process is requesting which resource. That means this entire diagram, resource allocation graph or RAG, resource allocation graph, represents the processes and resources, which process is assigned to the resource and which process is waiting for the resource. That is represented in this diagram. So out of all this diagram, the process P1 is waiting for the resource R2, that's showing that waiting for, and the resource R1 is assigned to the process P1, which showing that assigned to. So that means this entire deadlock resource allocation graph represents both processes and resources, which resources are assigned to the process and which process is waiting for the resources. That all we can represent in this resource allocation graph. In simple term, we can say that deadlock is represented in the resource allocation graph, where the process represents in the rectangle symbol and the resources are represented in the ellipse symbols. The conditions. To occur the deadlock, what are the conditions to be available? So what are the conditions that occur deadlock situation? And simple terms, the deadlock situations are deadlock conditions, also called as Kaufman conditions. Kaufman conditions. So for a deadlock to occur, all the four of these conditions must hold simultaneously. So all these four conditions has to satisfy. Then only the deadlock occurs. So the first condition is what? Mutual exclusion. So in this mutual exclusion, where a resource can only be used by one process at a time. So maximum is it is in shared mode, but each time only one process can allow to access that memory, access that resource. So at least one resource must be held in non-shareable state. So that means it does not, if it is in shared mode, it does not able to sharing for all the resources. It particular time the process has been only utilized only one time. So only one time or only one process at a time that can be utilized. And the second one, hold and wait. So where a process holds some resources while waiting for others. So when a process holding some resources and other process may wait for that resources. So a process must hold at least one resource while also waiting for other resource that are currently held by other process. So that means one process is in holding for the process and one other resources are holding by the next processes. That means they are under waiting. So that means one process in hold and other process in hold wait mode. And no preemption. So a resource cannot be forcibly taken from a process once it is been granted. The process must release it voluntarily. So if any resource is allocated to the process, that cannot be forcibly they are not being granted to deliver. So they have been released. They have been released must voluntarily. And the circular wait, where a set of processes are waiting for each other in circular chain. So like P1, R1, P2, R2, that is in a circular chain mode. So when a set of processes are waiting for each and every resource in a circular chain, a set of waiting processes must exit with the where P0 is waiting for the resource, and it is held by P1, and P1 is waiting for the P2, and P2 is waiting for the P3. Like that, all these are waiting in the circular manner. So P1 is waiting for the R1, R1 is waiting for the P2, P2 is waiting for the R3. Like that, all these processes and resources are in waiting in circular mode. So these are the four conditions. If all these four conditions are satisfied, then deadlock may occur. If we are saying that deadlock prevention conditions, that means we don't want to occur deadlock, we have to say no, or we have to say no, eliminate. We have to say no mutual exclusion, or we have to say eliminate mutual exclusion. So those are all the preventive conditions. So no mutual exclusion, no hold and wait, preemption, and no circular wait. So if we say no to all these conditions, then we can able to prevent the deadlock situation. Also we can write eliminate mutual exclusion, eliminate hold and wait, eliminate no preemption, eliminate circular wait. If we mention that eliminate also, we can prevent all these deadlock conditions that do not occur deadlock situation. So from this, the main thing, deadlock avoidance techniques. What are the deadlock avoidance techniques? What is meant by deadlock avoidance actually? So before occur deadlock, we have to identify the cycle. We have to identify the cycle based on the resource allocation graph. If any cycle is formed, then we can say that we can identify that deadlock is detected. We can say that deadlock is detected. So to avoid the deadlock, to avoid that situation of the deadlock, what we have to do? So that for that we have to propose two types of techniques. One is resource allocation graph algorithm, and the second one is Banker's algorithm. One is what? Resource allocation graph algorithm. Second one is what? Banker's algorithm. So obviously resource allocation graph is nothing but creating more number of resources, creating more number of resources for the particular processes. So already we've seen that deadlock is represented in the resource allocation graph itself, where all the processes and resources are in the mode. And the Banker's algorithms, where we can create more number of matrices, allocation matrix, maximum need matrix, available matrix. So from that, what we have to calculate? So that is one Banker's algorithm. So from this, we have to see the resource allocation graph algorithm. This technique used in when each resource has only one instance. So this algorithm works only for the each resource has only one instance. If the resources have multiple instance, this algorithm will not work. For that we can use Banker's algorithm. So this system checks the resource allocation graph before granting a request. So in this, the processes P represented by the circle, as we've seen in this previous chart. So the circles represented in the circles are represented in the chart. So the processes are represented by circle and resources are represented by square, and the request edge process requesting resources, and the assignment edge is in nothing but resource given to the process. So the direction towards the resources is requesting edge, and the direction towards the process is assignment edge. So all these processes under circles and resources under squares, and the requesting edge towards resources, and the assignments edges towards processes. So in this manner we can create more number of resources. We can create more number of resources like P1, and P1 is looking for the R1, and R1 is having assigned to the P2. Still P2 is looking for R2, and we can create more number of R3 also. If we create more number of R4 also. If we create like this more number of resources, if we create, if any process is in the deadlock mode, if any process is ready to occur in the deadlock mode, then we can assign to the other resources to do not occur deadlock situation. So here we can create more number of resources so that we can avoid the deadlock situation. So if allocating the resource creates a cycle, if we are not allocating, if you are not creating any cycle, then we cannot say that it is deadlock occur. But if allocating the resource creates a cycle, then the request is not granted and it occurs deadlock situation. It occurs deadlock situation. So here, suppose P1 requests R1, like P1 is requesting R1. This is the requesting edge. So requesting towards resource is what? Requesting edge. And the R1 is allocated to the P2. R1 is allocated to the P2. So the direction towards process is what? Assigned. And P2 requests R2. So P2 is requesting R2. So this is the requesting edge, and R2 is allocated to the P1. So this creates cycle. So to do not occur cycle, we can create one more resources so that deadlock will not be occur and cycle will not be occur, deadlock may not be occur. But in this case, the cycle occurs. So this creates a cycle, which means deadlock may occurs. So the system avoids allocating the resources. So in this manner, in this cycling creating manner, in this creating cycle manner, we cannot allocate the resources. So that what we have to do, we have to create more number of resources, like one more resource is created R3, that will be assigned to the P1, so that will not be created any cycle. So to avoid this, the create more number of resources rather than, that is the main thing we have to understand from this resource allocation graph. So if any process is requesting for the resource, or if any resource is allocated to the process, if it forms a cycle, if it creates a cycle, then the request is not granted and the deadlock may occur. If we create more number of resources, that will not create a cycle and the deadlock may not be occur. So this is the one technique, deadlock avoidance technique, creating multiple resources under the resource allocation graph. And the second one is what? Banker's algorithm. This technique is used when multiple instances, we already said that what? The resource allocation graph is only for the single instances of resource, but the Banker's algorithm for this multiple instances of the resource exist. So each and every resource having multiple instances like R1A, R2, B, R1A, R1B. So like that multiple instances that are created. It checks whether the system will remain safe after allocating resources or not. So after allocating the more number of resources, whether the system is in safe state or not, it checks. So first it identifies the need matrix, then it checks the process is in safe state or not. So basic idea of this Banker's algorithm is what? Before allocating the resources, the OS checks, if I give the resource, can I all process still finish eventually or not? Can I all process still finish eventually or not? Is it safe? It is completed or not? It is safely it is completed or not? It checks. If yes, the safe state. If it is check, is safe state. If it is not checks, it is unsafe state. The process is in not safe state, then it is said that it may occur deadlock situation. So here the data structures we used available matrix and maximum resources matrix and the maximum allocation matrix and the need matrix. So the thing that we can take number of free resources, that are number of available free resources, and the maximum resources are needed by the process, and the currently allocated number of resources for the process, and what are the remaining need resources to the processes. So from this we can find the need matrix first. We can find the need of the resources. How many number of resources are needed for completing our task. So for this we have the formula called need equals to maximum, that is the maximum number of resources needed by the process minus resources currently allocated. Resources currently allocated. So need equals to maximum minus allocation. So we'll take example. So available 2 by 2 matrix. The available resources are 1, 1 and the allocation matrix is what? 2 by 2 matrix. So here for the P0 the resources instances are available 0 and 1. For the P2 available resources are 1, 0. And for the maximum resources it can be utilized by the P0 and P1 is what? For the P0 1 resource 1 and instance 2, and for the P1 resource 1 and 1 instance. So from this above what we have to calculate? We have to find the need matrix and the safe sequence of the process. We have to find the need matrix and the safe sequence of the process. So how we can find the need matrix and how we can say that the process state is in safe state or not. So from this we have to calculate. So here the need equals to, what is the formula for need? Need equals to maximum minus allocation. So here need equals to maximum minus allocation. So maximum is what? 1, 2. So for P1 maximum is what? 1, 2 minus allocation is what? Allocation is what? 0, 1. Allocation is what? 0, 1. And for P2 maximum is what? For P1 maximum is what? P0 and P1. So for P1 maximum is 1, 1 and allocation is what? 1, 0. So from this we can calculate the need matrix. So 1 minus 0, 1, 2 minus 0, 1. And for P1 1 minus 1, 0 and 1 minus 0, 1. So this 1, 1, 0, 1 are the need matrix that we have to need more resources for the P0 and P1 instances. So for this P0 and P1 resources, P0 and P1 processes, we need more instances, like for P0 1, 1 instance is required and for P1 0, 1 instance is required. Now we have calculated a need matrix. Now we have to check safety check. So safety of the each and every process or not. So for that what we have to apply? We have to apply the condition like need matrix. Need is less than or equal to available. So what we required and what we have available. So what we required is less than or equal to available. That means what we are requiring, what we are needing is less than or equal to available or not. Is that required is available or not? That is the thing we have to understand here. So available is what? 1, 1. And what is the need is what? 1, 1. So need of P0 is what? 1, 1. 1, 1 is less than or equal to 1, 1. Yes, it is obviously satisfied. And for P1 need for P1 equal need for P1 0, 1 and less than or equal to available 1, 1. Yes. So process checks. So satisfied. So the need of the resources is less than or equal to available resources. Is the condition is satisfied or not? If the condition is satisfied, then it allocates. It allocates and after utilizing the CPU, it releases their CPU. So here the total overall available CPUs after utilizing the processes 1, 1 plus 1, 0 equals to 2, 1. So total available resources after completing the CPU utilization of the P1 and P0 processes is what? 2, 1. So the safe sequence is what? P1 to P0. P1 to P2. So P1 to P0. So the check P0 after finish it is okay. So the result is what? Safe state. It is in safe state because all the need are satisfied and the safe sequence is what? P1 to P0. So this is the way of we have to find the need matrix of the processes, and after finding the need matrix we have to check the safe state for the process sequence. If the safe state is available, then we can write the safe sequence of the processes. So now we state that the processes are in safe state. The safe sequence is P1 to P0. So this is the way we can understand the Banker's algorithm for the 2 by 2 matrix. And similarly for the 3 by 3 matrix, same available what? 3 3 2 matrix, and allocation is what? 0 1 0. These are all the instances, instance 1, instance 2, instance 3. So we already said that what? Banker's algorithm is for suitable for multiple instances that are created, and that resource allocation graph is only for single instances of the processes. So now these are the multiple, that means 3 instances for the P0, 3 instances, P1 3 instances, P2 3 instances. This is the allocation matrix for the P0, P1, P2, and the maximum allocation is what? P0 753, P1 322, P2 2902. So available we know, so allocation we know, and maximum we know. So from this what we have to find? We have to find the need matrix. Need matrix equals to, what is the formula? Need equals to maximum minus allocation. So what is the maximum and maximum? This one. So 753 for P0, 753 is the maximum, and minus allocation is what? 0 1 0. So what is the values? 7 4 and 3. This is the P0 need matrix. Similarly P1 need matrix. So P1 need matrix is what? Need matrix is what? 3 2 2 minus allocation is what? 2 0 0. So maximum minus allocation. So maximum 3 2 2 minus allocation 2 0 0. So 3 2 1 2 0 2 2 0 2 1 2 2. So this is the need matrix for the P1, and similarly for the P2 need matrix is what? So maximum is what? 902. 902 is the maximum, minus allocation. Allocation is what? 302. So 9 minus 3 6 0, and 2 minus 2 0. So this is the need matrix. So need matrix equals to, need equals to 7 4 3 1 2 2 6 0 0. So this is the need matrix. We can calculate it from the maximum minus allocation. So check with this. 7 4 3 1 2 2 and 6 0 0. So 7 4 3 1 2 2 6 0 0. So we found need matrix. The next what we have to do? We have to find the safety check. We have to find the safety check of the process. So to test this safety check, what is the formula? The need matrix is less than or equal to available. So need matrix is less than or equal to available. So now you can check. So available is what? 332. So need for P0 equal to 743 is less than or equal to available 332. Is this condition is satisfied or not? Not. Next P1. So for P1 need equals to 122 is less than or equal to 332. Yes, it's satisfied. It does not satisfied. P1 is satisfied. And for P2 600 less than or equal to 332. Is this satisfied? No. So only P1 is satisfied now. So the safe state starts with P1. So it starts with P1. So then how P0 and P2 will be satisfied? How P0 and P2 would be satisfied? So after P1 utilizing these P1 resources, is what? P1 resources are 200 is allocated to the available resources. So 332 is the available resources, and 200 which are completed P1 200 will be allocated to this one. So total 532 are the available resources. Then next check P2. So 600 is less than or equal to 532. 600 is less than or equal to 532. Is this condition is satisfied or not? Not. So but with most processes normally you will not find. So assume safe sequence existed. So P1 is existed and P2 is not existed and P0 is not existed. So the safe state starts with P1 and P0 cannot satisfied and P2 also cannot wait. So till they have to wait. So more processes are normally you do not find. So assume safe sequence is existed the safe sequence starts with P1. Safe sequence starts with P1. So this is the way of understanding the banker's algorithm. So checks the banker's algorithm and where the number of processes are available and where the number of resources are needed. So that condition is to be satisfied. Need less than or equal to available. So where the need is less than or equal to available satisfies, then the condition starts with P1. Condition safe state starts with P1. So this is the way we can understand the banker's algorithm. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.